I'm going to talk about the Constructal Law a bit. Constructal Law is the most recently discovered thermodynamic law, and it is about how flow systems that are far from equilibrium evolve. It states that flow systems that are far from equilibrium evolve to increase the flow and the access of the flow. So in terms of the Earth's climate, what does that mean? Dr. Bajan and Dr. Adrian Bajan developed a theory that the Earth's climate system, in a constructal sense, is evolving to increase the flow of energy from the hot area around the tropics and the equator to the cold area in the poles. So in this model, we have two areas, AH and AL, the hot area with temperatures TH and TL. And the basics of the model are, in the hot area, you have energy coming in and energy going out, and there's leftover. It moves to the cold area, where it's added to the energy coming in, and it goes out. So there's a constant flow of energy going from the tropics to the poles. How does that look in the real world? Well, these are the actual hot and cold areas of the real world. The orange areas are the areas that are exporting heat. The blue and green areas are the areas that are receiving heat. And in agreement with the constructal model, this shows that it's relatively symmetrical, that the areas of the cold are about the same size on the north and south poles. Now, in the model, there is a straight line across there because it's just a model. Now, be clear that this model has no oceans, has no mountains. It's just a simple sphere illuminated by constant sunlight. There are four unknowns calculated by this model: the average temperatures of the hot and cold zones, the area of the hot zone, and the power flow that's going from the hot zone to the cold zone. There are three tuned parameters: the conductance, which is how easily the flow goes, the power absorbed in the hot and cold zones. There are four governing equations. In the hot zone, you have power in minus power out is the flow Q. In the cold zone, you have power out minus cold zone power in. That's also Q. The conductance is a function of the difference of the temperatures, and there's a constructal constraint that the flow is maximized. There's four real-world inputs: the albedo and the greenhouse factors for the hot and cold zones. The greenhouse factor is what percentage of the radiation from the surface makes it out to space. The albedo, of course, is what percentage of the incoming solar energy is reflected back to space. This is a movie I made of how the hot and cold zones vary over time. The answer is hardly at all. Year by year, these are the differences. There's some differences on the west coast of the North and South America, but in general, especially over the land, it's pretty well established. And even over the ocean, it doesn't change a whole lot. This is rainfall as a proxy for thunderstorms in the tropics. This is one of the big differences between the real world and the model. In the model, the overturning is just driven by the temperature difference. But in the real world, we have this band of thunderstorms that's driving the air upward and towards the poles and carrying immense amounts of heat. So, how well does the model do? Well, This shows the calculated temperatures, not anomalies, but actual temperatures from this model. This is from the series satellite data, hot and cold temperatures, and the modeled hot and cold temperatures. You can see that around the year 2010, there are some slight differences, but at this scale, you can't see any difference at all. This to me is pretty amazing because it takes so few actual inputs and it does such a good job. Now, is it tuned? Yes, it's tuned, but only for the difference between the hot and cold zones. Given just the difference between the hot and cold zone temperatures, it calculates the actual absolute temperatures. This is a close-up of the top one there. You can see again that around 2010 it's slightly larger. But overall, the model does an excellent job of showing the changes in the hot zone temperature. This is the same thing for the cold zone temperature. In both the hot zone and the cold zone temperatures, the main difference between the model and reality is that the swings are larger in the model. And I ascribe this to the fact that the model assumes that all the swings are due to temperature swings, where in reality, that's not the case. Some of the swings are due to things like the atmospheric window, which lets some of the upward radiation just escape directly to space. So we have good agreement here. Now, this is the actual and modeled power flow. Those are quite different. Why is that? Well, the reason is that if we go back to this here, you can see that there are large areas, desert areas in Australia, in North Africa, and in the Gobi area, and the area of Saudi Arabia that are actually in the cold receiving area, but they're not in the model. Those areas are not in the model. So that gives us a fairly large difference in the absolute values of how much power flow there is. But when we go and look at the anomalies, that's what the model predicts. That to me is quite astounding, that such a simple model with so few inputs gives such a close answer to how much the power flow is. And to me, this is excellent confirmation that the constructal model, which says that the Earth's climate system is not just a pool table where you strike a ball and it goes somewhere. It is constantly evolving to maximize that energy flow. It responds to the changes. It's not an inanimate kind of thing. It is constantly modifying and evolving to respond to changes in the albedo and respond to changes in the greenhouse factor. This is the other thing that's predicted by the model, which is where the boundaries are for the hot zone. The series hot zone boundaries and constructal model hot zone boundaries, again, they're slightly different because, same reason. In the real world, there are areas which are in the hot zone in the model but are in the cold zone in the real world. But once again, it does quite a workmanlike job of showing the changes in the area of the hot zone. And here is the predicted and actual hot and cold zones. The actual and the model hot zone The model hot zone is shown by the dotted yellow lines, top and bottom. The real hot zone is the white and black lines, and they're quite good. To take this further, I took a look at what doubling the atmospheric CO2 might do. So I recalculated the greenhouse factor by simply adding 3.7 watts per meter squared from the putative doubling of CO2. The model calculated increase in temperature was 1.1 degrees C per doubling in both the hot and cold zones. It was slightly different, 1.06 versus 1.14 or something like that. So that's quite small. It's not the smallest, but it's extremely small, and that drawing is not correct. Those lines should be higher up. I'm not sure why they're not. But I say that that is a maximum climate sensitivity because all I varied is the greenhouse factor. I didn't vary the albedo. And of course the albedo, because this is a dynamic system, the albedo will be changing as well. These are the shortfalls of the model. Here are the boundaries of the hot zone and the average area error in the flow. I think that it's related to the stable Sahara, Arabia, China irregularity. Further challenges: find the reasons for the larger swings in the model temperatures and explore the monthly variations. Improve the model by including the sensible and latent heat loss in the atmospheric and absorption of incoming sunlight and the surface transmitted irradiance. A few comments on this. First, it makes perfect sense. Albedo regulates how much energy enters the system. The greenhouse factor regulates how much energy leaves the system. The balance between those two is what we would expect to regulate the temperature. And this model shows that actually that's what's happening. Second, it shows that the greenhouse effect, the greenhouse factor, is a real quantity that needs to be taken into account. It's not of the size where it's any kind of danger. Like I say, my calculation, simple calculation, shows that climate sensitivity at near the bottom, and I think that the sensitivity is actually lower due to the response of the albedo. Next, I've long held that the thermostatic effect of the thunderstorms and other emergent phenomena is critical. This supports that because the albedo and the greenhouse factor, more than anything else, are factors of the clouds. The albedo, of course, is mostly changed by changes in the clouds, and the same is true about the greenhouse factor. So that is my presentation for today, and I would sum it up by saying that all of the current climate models are working in the wrong way. They assume that all possibilities are equally possible. They assume that the climate is some kind of fixed system where if you add a little here, everything has to change in a predictable manner. The system doesn't work that way. It works in a constructal method where the system is constantly evolving to maximize the throughput of energy. And until the climate models start dealing with that, we're going to have the same problems that we have with them, which is that they are basically tinker toy models that are used for political purposes. Thank you.